Okay, so let's talk about inverses of holomorphic functions. This is sort of, another one of these sort of now rapid fire results, because now we have all this machinery and we can just, prove results one after the other, right? So now we can say more about inverses of holomorphic functions, and they actually have some rather interesting interesting properties. So let's start by maybe the basic version. So this, you've seen this theorem before, except there's one thing that I've left out of this theorem, and that's before in the notes where it appears. There is an extra hypothesis that says that that f had better be continuously differentiable, but we already know that all holomorphic functions are continuously differentiable. So what the inverse function term says, in a nutshell, is that if you have holomorphic functions and the derivative at some point is non-zero, then locally we can invert that function. Maybe not globally, but locally we can invert that function near that point, right? That's what the inverse function is. I mean, the function theorem is for any type of functions, but in this case we get holomorphic functions, and the inverse is holomorphic. So that's the inverse function theorem, right? So again, this is just global. Local. It's not global. If we take, let's say, the punctured complex plane, then z squared maps the punctured complex plane to itself. The derivative never vanishes, and the function is not one-to-one globally. It's one-to-one locally, right? Near every point there is a neighborhood such that it's an injective mapping onto onto a small neighborhood, and it's one-to-one. It has a holomorphic inverse, right? But not globally. Globally, there's to every point there's exactly two guys, two square roots, right? All right. Now, for real functions, just any real, non-holomorphic functions, really what I mean, is these functions can be injective and the derivative can vanish. For example, x cubed is an injective mapping, but the derivative at 0 is 0, right? So it has an inverse. The inverse is not differentiable, right? Its derivative will blow up at the origin, right? The derivative of the inverse, right? It's the cube root. But this does not happen for holomorphic functions. For holomorphic functions, essentially, holomorphic functions are like z to the k, and in the complex plane, z to the k is injective only if k is 1, right? So z cubed, just to take it back to this example, z cubed is not injective in any neighborhood of the origin. It is actually basically 3 to 1, except it takes 0 to 0, and it's the only point that gets taken to 0. But you can sort of think of it with multiplicity. So it's really 3 to 1. Now, so this means that for holomorphic functions, because if z to the k, if the only z to the k that is injective is when k is 1, and all holomorphic functions are locally basically like z to the k, then the derivative should never vanish for an injective function, right? Because the derivative of just z to the first power z, derivative never vanishes, and that's true. If you have an injective holomorphic map, f prime does not vanish. So let's prove this. Suppose f prime vanishes somewhere, and let's suppose that it's a non-constant function, which we're going to prove it by contrapositive. We're going to show that if f prime vanishes, then f is not injective. All right, so let there be a small disk around P, small closed disk, such that f prime does not vanish in this entire little disk, right? Except at P, of course, right? Because at P it does vanish, but let's suppose that it does not vanish anywhere else, and we can do that. It's non-constant, so f prime cannot be identically zero. And furthermore, we have that f is non-constant. Again, just like before, we can it's an isolate. Fz minus fp. That as a function of z that has an isolated zero, and therefore I can find a delta such that fz minus fp modulus is bigger than some positive delta on the boundary of this little disk. It's basically just like we just did with the open mapping term. It's a very similar proof. And now this mapping, this function f of z minus f of p, well, it has a zero. It has a zero at least of multiplicity 2. Why is it at least of multiplicity 2? Well, that's because this function is 0 at p, right? Also, its derivative, which is the same as the derivative of f, actually, right? Because f of p is constant, right? So the derivative is not 0. The derivative, this is what I wanted, the derivative is equal to 0 at p, right? So therefore, if I have a function, it's 0 and its derivative is 0, it has 0 of multiplicity at least 2 at that point, right? And so now take w in this delta disk, suppose it's not f of p, just any other w, and we apply Rouchet just like we did with the open mapping term. It's the same exact proof, and we get that f of z minus w and f of z minus f of p have the same number of zeros. But now we have that f of z minus f of p has a zero of multiplicity at least 2. That means that up to multiplicity, f of z minus w has at least 2 zeros up to multiplicity in this disk. Now, we're not quite done yet, right? Because, well, maybe we just have a zero of multiplicity 2. We really need 2 distinct zeros. But for this, we notice that, well, f prime is non-zero in this entire punctured disk, right? It's only 0 at p, right? And that's f prime is again the derivative of f of z minus w, right? And so that function, it's all the zeros except the zero at the it doesn't have a zero at p, but if it's all the possible zeros of f of z minus w are simple, right? Because so those two zeros that we found have to be simple zeros. That means that they have to be distinct, right? Because you can have if all the zeros are simple, then the only way that you're going to get 2 zeros is if they're different, right? You cannot have a larger multiplicity 0. Well, that means that f is not injective, right? Because, well, there's f of z minus w has at least, that's f of z minus w equals 0 has at least 2 solutions z in this disk, right? Okay, so So therefore, f prime. If for an injective map, f prime is never 0, right? Now we can actually compute the inverse of an injective map. So we have the following lemma: if f is holomorphic and injective, and we take a closed disk in U, then for all W in the image of this disk, we actually have a formula for the inverse inverse value, and it's basically this integration around the boundary of this disk, right? It's almost like a Cauchy integral formula for the inverse, right? And the formula is just in terms of f, well, and f prime, but it's just in terms of the values of f. All right, so the proof of this formula is well, let's fix some w in this image, and let's let the zeta be the point that goes to w, right? So that f of zeta is equal to w. Now, f prime is never 0, right? Because, well, we just proved that, right? It's an injective map, so f prime is never 0. So that means that f of z minus w has a simple 0. It's precisely at zeta, right? That was that's the way that we picked zeta, right? And it has to be a simple 0, right? Because f prime was never 0. And now we just apply the residue term, right? So it's you take this formula, this maybe sort of magical looking formula, and say, well, let's compute it using the residue term. It's what's inside this integral is well, that's going to have a simple pole at zeta, right? And it's not going to have any other singularities, because that's the only 0 of the denominator, right? F is injective, right? It can only have that can only have a 0 at zeta, and we know that it's a simple 0 because f prime is never 0, right? So therefore, this is a meromorphic function with a single pole, and it's a simple pole, and we're computing basically something that's exactly that's what the residue term is made for, is to compute these sort of integrals. And so the residue term says, well, it's the residue of what's inside at zeta. Now that's actually easy to compute, right? We had this this proposition that if we had a holomorphic function of a holomorphic function, and the 0 of the denominator was simple, then to figure out the residue, we just evaluated the numerator, and we divided it by the derivative of the denominator evaluated at zeta, and that's precisely what we do here, right? It's the numerator evaluated at zeta and the derivative of the denominator evaluated at zeta, right? And you actually figure out that the f prime and zeta cancels out, and we just get zeta, which is precisely what we needed. That was exactly the inverse of w. That's the way that's what we define zeta to be, right? So that's what we want this integral to be. All right, so this tells us that there is a formula, right? A really nice integral formula for the inverse just in terms of f, okay, and f prime, right? So if we know if we know f, we can just stick it into this formula, and we have a formula for the inverse. Now, if we put these two lemmas together, I mean, we clearly get more out of this, but if we put these two lemmas together, we get the following result, which is maybe that's really the main result of this section, and that's and if we have an open set U, we have a holomorphic, injective holomorphic map F, then the image of U, F view is open, F prime is never zero on U, and the inverse mapping is holomorphic, right? So we just need, basically for biholomorphisms, we just need injectivity. We get automatically that F prime is never zero, and we get automatically that the inverse is holomorphic. Right, so if we have a holomorphic function, we want to see, is it a biholomorphism? We only need to check injectivity. We only need to check that it is 1-to-1. So let's prove this. Suppose suppose we have a U and an F like this. Well, FU is that's the open mapping term, right? That we just proved that f of U is open, right? Because U is open. By the first lemma, f prime is never zero. So again, we just proved that, right? So now the second lemma, and this is maybe a bit more. This is the still complicated part of it. The second lemma actually says that f inverse is holomorphic. Why does it say that f inverse is holomorphic? Let me maybe go back to the lemma. Well, it gives us that f inverse has at every point. We just need to locally to show that it's holomorphic, right? It's a local result. But if we have this formula, right? So near we look at P, and we look at the image of P, and near the image of P, we have this formula for the inverse. And if you look at what's happening here, this is we have a function out here of we're integrating in terms of z, and but it's also a function of w, and it's a holomorphic function of w, right? And we've proved before. I mean, we needed it. We needed this result before, that if we integrate. This is one way to show that the Cauchy transform was holomorphic, right? If we integrate something against a function that's holomorphic in some variable that's not being integrated against, then this is holomorphic, right? And again, it's to prove that there's if you remember, that was we could either apply Moreira's theorem, right? That was one way to prove that that lemma, or it was differentiating under the integral, right? You could take the W bar derivative, right? Apply the Cauchy-Riemann equations to this in terms of W, right? And get that this expression has to be holomorphic in W, right? So So that's why this this last last part of this proof, we get that that F inverse is in fact holomorphic, right? So this is the main idea of this section that we're covering. I guess 5-6 in the notes. That if I have an holomorphic injective map, then the image of U is open, so therefore I have a function defined in an open set. The inverse F inverse is defined in an open set, goes back to U. F prime is never zero, and F inverse is holomorphic. Of course, F inverse is also injective, and therefore its derivative also is non-zero. You just you just apply this term again to F inverse if you want. So, all right.